Hello and welcome. In this video, we will review the basic concepts of integration. You should have printed out this review of integration handout and be ready to fill in the blanks and follow along with the lecture. Let's begin. Remember that there are two fundamental kinds of integrals. There are definite integrals and there are indefinite integrals. Definite integrals have this form. We have the integration symbol, and then we have the a and the b, which are called limits of integration. We have some function f of x, which is called the integrand. And recall that definite integrals correspond to the area between the function f of x and the x-axis. Let's illustrate this. Let's think of some generic function f of x. Maybe it looks something like this. And let's take a value a over here and a value b. So we're thinking of taking the area between the curve and the x-axis. The area above the x-axis is counted as positive. Area taking below the x-axis is counted as negative. The integral finds the area of these two regions, adds them together, and we can imagine that would probably be close to 0 for this particular sketch because the positive area looks about the same as the negative area, but the integral would take that into account. So that is a definite integral, area between the curve and the x-axis. The other main type of integral is an indefinite integral, and there's another name for these. They are also called antiderivatives. So let's really quickly write down what an antiderivative is. We say that a function capital F is an antiderivative of a function small f if the derivative of capital F equals small f of x. Another way to notate this is to say that capital F equals the integral or the antiderivative of small f. So we're taking the concept of derivatives from Calculus 1 and we're completely reversing it. Instead of saying what is the derivative of this function, we say if we're given a certain function, what function has this as a derivative? So we're finding the antiderivative of the integrand. Now, at first, the concept of areas between curves and antiderivatives do not look related. They seem separate concepts. However, the fundamental theorem of calculus part 2 relates these concepts together. Definite integrals and antiderivatives are related using this theorem. Capital F of b minus capital F of a, where once again, capital F is the antiderivative of small f. This is not the definition of definite integrals. It's a theorem that shows the relationship between definite integrals and antiderivatives. So this is an important concept. We need to find antiderivatives in order to solve definite integrals. And it's very important as we start Calculus 2 to know the basic integral rules. We will rely on a strong knowledge of the fundamental integration rules as we start looking at integration techniques. Now, let's look at an important perspective. Let's think of the difference between derivatives and integrals. Taking derivatives is a process. We have derivative rules like the quotient rule, chain rule, product rule, all these different derivative rules. And once we learn the derivative rules, it's just a process to apply them to certain problems and find derivatives. In some sense, there's no such thing as a difficult derivative problem. They can get complicated. They can get a little bit difficult to work with as far as the complexity, but we can always take the derivative of any function. Integration is a completely different concept. Solving integrals, I like to think of it as an art. So we have differentiation rules. We just follow the rules, but we have integration techniques. An important component of Calculus 2 is learning the integration techniques and understanding the situations in which it's appropriate to apply them. Another way I like to think of this is to think in these terms. It is always possible to find derivatives. We simply follow the derivative rules. However, it is not always possible to find an antiderivative or an indefinite integral in terms of a closed form. It is not always possible to find an antiderivative. Now, the function may have an antiderivative, but we might not be able to express it in terms of our elementary functions like sine, cosine, exponential functions, log functions. We might not be able to write a closed formula for the antiderivative. Let's take a look at this in Mathematica. All right, so here we have several integrals. We have the integral of e to the x squared, the integral of sine of x over x, and the integral square root of 1 minus x to the fourth. These are not terribly complicated functions, and if we thought of taking the derivative, we could take the derivatives of these functions. We'd have to use chain rule, we'd have to use a quotient rule, we'd have to use another chain rule, but we could take derivatives fairly easily here. However, taking the integral or the antiderivative of these functions is a completely different matter. Let's see what Mathematica gives us for the integral of e to the x squared. We have 1 over 2 square root of pi, and then this ERFI, ERFI. All right, let's ask Mathematica what this ERFI is. ERFI is the imaginary error function, whatever that is. And if we explore this a bit further and just look at the regular error function, if we look at the details here, we'll notice that the error function, which is related to this ERFI error function, the error function is actually defined in terms of an integral. That means that this error function doesn't have a closed form expression in terms of fundamental normal functions, such as sine, cosine, exponentials, logarithmics. All right, let's look at the integral of sine of x over x. We have the sine integral of x. Sine integral is the sine integral function. If we look at the details here, we can see that the sine integral function is defined as an integral. There is no closed form expression for the sine integral function. We can't write this in terms of elementary functions in a closed form fashion. There is an antiderivative, but we can't write it out nicely in terms of elementary functions. Let's look at the last one as one more example. We have a very complicated expression here involving elliptic f with arc sine. What is elliptic f? The elliptic integral of the first kind. Again, if we look at the details here, we'll see that the elliptic integral is defined in terms of an integral. So we cannot express the antiderivative of this relatively simple function in terms of our standard ordinary functions. This illustrates that integration is fundamentally different than derivatives. We can find the derivative of any function in terms of elementary closed forms, but the antiderivative we can't always write in terms of elementary functions.